So I'm going to get started because we have to get through chapter 23. So the chapter 22 homework will be due on the 3rd. That's Friday. The chapter 23 homework will be due on the 10th. That's next week, Friday. The chapter 22 quiz is today in SI. Because we're having a test next week, we don't have time to do a chapter 23 quiz in SI in order to have the test before midterms. That's more or less why it's squished like this. So the chapter 23 quiz will be on Blackboard today at 11 starting at 10 a.m. Until the 9th. So you have a week for it. It'll be timed. You have 40 minutes and then it will automatically end. It's 25 questions like the other quizzes. It needs to be done in one sitting. You get one attempt. And the short answer questions on it have to be graded manually, so your grade may not pop up immediately. Because I have to go through and grade them. But they'll get graded soon and your grade will pop up. The exam on the 8th will be on chapter 1 and chapters 21 through 23. You'll get one sheet of notes. You will need a calculator. It's mostly multiple choice with some short answers, much like the quizzes have been. And additionally, there will not be a lab next week. If you need to make up labs, you can make up labs then. I think that is all. Okay. Daily rate. So we're on finishing off chapter 23 because we need to get it done today. And I think we're a little behind. So we talked about the zone of aeration and the zone of saturation, where the zone of aeration is the part of the ground that has air in it. And the zone of saturation is that part of the ground that's completely, where all the holes are completely full of water. Due to gravity, some of the water at the Earth's surface will slowly percolate through the unsaturated zone of aeration until it reaches the zone of saturation. And the boundary between these two zones is the water table. If you want to find the water table, basically you dig down until your hole fills with water naturally. Within the zone of aeration, air partially or completely fills the pores. Within the zone of saturation, water completely fills the pore spaces. If the zone of saturation has enough porosity, holes in it, and permeability, it can flow. It forms an underground reservoir of water that can be tapped by drilling wells to depths below the water table. Basically, if there's a reasonable amount of water in the ground, if there's enough holes and enough flow, you can pump it out with a well. You drill a hole down and pump it out. You could just dig a hole down and take it out with a bucket, but we usually pump it these days. Additionally, lakes, streams, and springs are found where the water table intersects with the surface. So, around here, the water table is not very deep at all because it's going to be at about the same level as the lake. And well, the lake is not very far down from here. And the water table will display seasonal variations. It can dip below shallow wells during a dry spell. This can be a real issue. If your well isn't deep enough, you can have it dip below shallow wells. You can also have, if some neighbor of you digs a really deep well and pumps a lot of water out, that could actually lower the water table around the well enough to dry your well up. So if you have a body of permeable rock that both stores and holds groundwater, that's called an aquifer. So things like sand, gravel, porous sedimentary rocks, these make good aquifers. And most aquifers require pumping by wells. Because usually the water's underground, you have to pump it up. So you can have some aquifer, these are called water table wells. It is possible to have an aquifer that's under pressure, where you don't actually require pumping. that's called an artesian well. But here is a water table well. You have a pump going to the water table. There's the zone of aeration, the zone of saturation, the water table. The water table will sort of move downhill towards streams and other things. You can see things like this out. Wells, wells just like this are in many of the forest preserves around Cook County. In some situations, groundwater will flow to the surface under its own pressure. This is called an artesian well. This happens when the aquifer is trapped. So if your aquifer is trapped beneath some impermeable layer and it's fed uphill and filled up uphill, the water table, so some aquifers are sandwiched between a pair of sloping and impermeable rock layers. This is called a confined aquifer. And if the higher end of this aquifer is exposed at the surface and receives water, wells penetrating the downslope aquifer can flow under their own pressure. So basically you have somewhere up a hill, water is going into the aquifer, it's trapped between two impermeable layers until you get to so you have an open area at the top, two impermeable layers, it's trapped in between, and then eventually at the lower layer, water comes up and out. And this, an artesian well, we recreate this artificially with our plumbing systems. This is what water towers do. You put water up in a water tower to create the water pressure that drives the water coming out of your walls of your house, etc. So this is sort of a natural version of that. Here is a video about aquifers. And now I'm getting this error here. Well, maybe this is more universal. Maybe YouTube made a change.
There are about 200 aquifers in New Zealand.
Oh, shit. Come on.
Aquifers in Hawke's Bay are the lifeblood of a region reliant on primary production. Aquifers feed lakes and rivers. They receive water from rainfall and river connections, channels and drains. Areas of saturated rock or sediment store water in pores and cracks in sands, gravels and rocks below our feet. An invisible taonga, but essential for our environment, our productive communities, towns, cities and industry. Water travels and filters through underground layers, moving with gravity to surface waterways and finally the ocean. Some aquifers are confined between impermeable layers of sediment or rock, and groundwater can be under pressure, sometimes so much pressure that it will flow above ground level in a bore without pumping. The main users of groundwater in Hawke's Bay pump water from below ground to supply town water, industrial uses and irrigation. Much smaller volumes of groundwater are also used for frost protection, private household supplies and water for stock. Too much groundwater pumping can remove essential water from rivers and streams, so less space for fish, river life, recreation, even lower groundwater levels. The size of an aquifer is less important than how it is managed. The key is to protect groundwater levels and connected surface layers of streams and rivers from overuse. Aquifer water is also vulnerable to contamination by disease-causing microorganisms, as well as from excess nutrients, pesticides and other contaminants. Hawke's Bay Regional Council relies on specific rules, limits, landowner groups, sector support and catchment-based expertise to manage water quality and quantity now and for the future.
Let me just try. Okay. That's going to be really annoying if that's a real problem. So groundwater supplies are a limited resource. Water tables will drop during dry seasons and will also drop. The rate of extraction from water wells is too great. And in order to maintain a stationary water table, water has to be replaced into the aquifer at the same rate that it moves out of the aquifer. So recharge is the rate of water replacement into an aquifer. And the source of recharge is precipitation and or flowing streams at the surface. So rain and water absorbed from streams, things like that. And lots of aquifers, many aquifers are getting depleted due to high extraction rates, particularly by agriculture and industry. So the Ogala aquifer of the central US is a good example of recent aquifer depletion. This aquifer received most of its water over 10,000 years ago during the wetter climate of the last ice age. And the natural recharge of this aquifer can't keep pace with over the 150,000 wells that are constantly extracting water for agricultural use. Modern agriculture uses an enormous quantity of water. Now, water within the zone of saturation helps support the overlying weight of the strata. So if you pump out all the water, there's less there to help support the overlying weight. You can actually have subsidence. The overlying strata will begin to compact and the ground surface will subside. And this can lead to shifting in building foundations, ruptures in pipelines, and cracks in roads. And in low-lying coastal areas, subsidence can actually lead to flooding because you get lowered low enough that you easily flood. Additionally, in most coastal areas, the groundwater is separated by density. Fresh water is less dense than salt water and therefore tends to stay on top of the salt water. And if you excessively withdraw fresh groundwater, this can result in salt water being pulled up into your well bore. And once you get salt water pulled into your well bore, the well will be ruined and the level of the water table will change. Basically, once the salt water gets up there, it's going to stay there. It's not going to really retreat. So here you have fresh groundwater sitting on top of salty groundwater near the coast. And if you overly pump, you pump all the freshwater groundwater out and the salty groundwater moves in. And then suddenly your well is contaminated with salt and there's nothing you can do about it. Now, numerous problems occur when aquifers have too much water extracted or the extraction rate is too rapid. Things like water tables get lowered, ground subsidence occurs, and in coastal areas, saltwater contamination is possible. So it's very important to manage groundwater reservoirs well, because you don't want to destroy your water supply. You also want to be careful about not polluting your groundwater supply. Contaminating your groundwater supply can also be a problem. So groundwater contamination also occurs when other substances percolate down into the zone of saturation. So this is an issue around here because we have all this old industry. So you could have industrial and household chemicals percolating into the zone of saturation, things like fertilizers, pesticides, sewage, herbicides, detergents, refined petroleum products, and other things like that. If they get into the groundwater could end up contaminated. Everything involved doesn't move very fast, so it will stay contaminated for a long time. And water quality can be adversely affected depending on what the pollutant is and the concentrations present in the groundwater. So, like biological stuff, like sewage, is probably it's bad, but it's not that bad because that'll clear itself up over time. And if the aquifer is of the right type, it'll actually act as a filter and can deal with it. So water is treated to make it safe to consume. So municipal water supplies are generally treated with chlorine to kill bacteria and viruses, but chlorination does not remove chemical pollutants. So chemical and mineral pollutants in the groundwater have to be removed by some filtration or chemical process. So here is a video about a wastewater treatment plant. Yep. This is going to be a problem all of today that I do not know how to fix.
Where does it all go? You just push the lever and it's gone. It's not magic, But it is pretty weird that everything disappears. How does it all work? Can anything go down there? Are there even any rules? And is the sink any different? The bathroom sink, the kitchen sink? Actually, there is no difference. Sink, toilet, same thing. Behind these walls and under these floors, all the drains meet up in a single pipe and head toward the sewers. Take a look at this. No, not that. This. What happens down here is pretty cool. Everything that leaves the house through the main drain pipe meets up with the sewer, right down here. In some places, it's a combined sewer, both wastewater and stormwater. In other words, everything from inside your house and everything from outside your house, rain, whatever, goes into a single combined sewer. All of it heads towards the wastewater treatment plant. In some places, the sewers are separated, one for wastewater and the other for stormwater. In that case, only the wastewater heads towards the wastewater treatment plant. The storm sewer goes straight to the Detroit River, untreated, because it's only water, right? Actually, no, it isn't. All the chemicals that you put on your lawn or the soap with all the phosphates that you wash your car with all head out in the storm sewer if you've got a separated system. Straight into the Detroit River. Some people hook up their downspouts to their main drain so that they can keep water away from their home. The problem is, when you add all that rainwater to the dedicated wastewater sewer line, it can overload the system, and during a heavy rainfall, homes can be flooded. And a portion of the wastewater will have to bypass the wastewater treatment plant because it's overloaded and head straight into the Detroit River. Instead, you can just disconnect your downspout and add a rain barrel. Simple as that. But simply adding a rain barrel isn't enough to protect the system. Let's hear from the experts about some of the other things we should think about.
People put things down the sewer that aren't supposed to be there, for example, oil and grease.
You pour it down your sink and it's liquid. With hot water, you think, it's fine. It's gotta go somewhere and it solidifies.
Sewers can get plugged up, which could lead to basement flooding of your own residence or a neighbor's residence. Your toilet or your sink is not a garbage can. Municipal wastewater treatment plants were never designed to treat chemicals that could be in your pharmaceuticals or your personal care products.
Paints, oils, solvents should be in containers and disposed of separately, not down the sink or the toilet.
Pharmaceuticals can go back to the pharmacy.
Flushable wipes for children, for example, physically they are flushable, but they're not in the water long enough to actually degrade, and they do clog the pipes. Sanitary napkins and tampons, women flush down the toilet thinking that's fine, that's what they've always done, but those do clog the sewer systems and cause issues elsewhere.
Products like that should be in the garbage. Food waste, composting, or the garbage is the better way of dealing with items like that.
So, to sum it up, a storm sewer is not a garbage can. Only rain goes into the storm sewer, nothing else. If you pour your bacon grease or cooking oil or anything like that down the sink, it'll most likely end up clogging the sewers on your street because oil and grease become solid quickly. You should let grease cool down, put it in an empty container, and throw it in the trash. Or even better, take it to the Essex-Windsor Solid Waste Authority's public drop-off depot at Central Avenue and EC Row. And speaking of which, that's the same place you should bring motor oil, unused paints, and things like that. Don't dump them in the sewers. The toilet and sink are no place for unused pharmaceuticals. And look for the Eco logo on cleaning and personal care products. If you flush things that shouldn't be flushed, wipes, feminine products, those kind of things, they'll clog sewers. Even if they say flushable, they're not. And when the sewer is blocked, people's homes flood because wastewater has nowhere to go but back up to the house. So, let's heed the experts' advice. We need to think before we clog the sewers, misuse the wastewater treatment plant, or harm the Detroit River. Oh, and speaking of the wastewater treatment plant, I think it's time we take a look and see what goes on down there. All the wastewater from the city of Windsor ends up at one of two wastewater treatment plants. The Little River plant, or in this case, the Lou Romano plant. The purpose of each of these plants is to remove all solids and pathogens, microorganisms like bacteria and stuff, from the wastewater, so when it gets reintroduced to the Detroit River, it's cleaner than when it arrived at the wastewater treatment plant. When it arrives, coarse screens remove large solids, rags, and debris from wastewater and are immediately disposed of. It's here that you see some of the most ridiculous things people have put down their toilets, drains, and sewers. At least this stuff made it this far. Some things that the water can't dissolve end up stuck in the sewers, leading to sewers being clogged and homes being flooded. After this, fine screens are used to remove the smaller material in the same way. Next up is grit removal. Grit includes sand, gravel, and other heavy solid materials that are heavier than the organic solids in the wastewater. Removal of grit happens by getting the wastewater to flow in a spiral pattern. Heavier particles settle at the bottom of the tank, while lighter organic particles are suspended and eventually carried out of the tank. From there, that water is sent into a settling basin. This is where suspended solids settle out and floating scum is removed by skimmers. Scrapers in the tank move continuously along the bottom to deposit the raw sludge into hoppers, which is sent to a nearby plant where it's made into pellets for fertilizer. After the settling basins, the wastewater is sent to the next step by an Archimedes screw pump, which forces the liquid upwards. The revolutions raise the water thread by thread until it comes out at the top of the cylinder. There, it is met by the fine curve screen, where small items that have made it through the initial screening process are removed. Things like fruit and vegetable stickers. They don't dissolve and they clog up the system, so when you're peeling them off, throw them in the garbage, not down the sink. Now it's time to get the stuff you can't see. Some of this work is done by biological aerated filters. Essentially, what happens here is that good microorganisms attached to porous rock eat up the bad microorganisms. The wastewater is pumped up through the rocks and the bacteria in the water sticks to the rocks. Bubbles are pumped in to keep the good bacteria alive and working. The clean water goes up and the rocks with the bad bacteria attached to them go back down. This cleansed water then flows into a channel on its way to be treated by ultraviolet light. The water passes high-output UV lamps, where light disrupts the molecular structure of DNA molecules in the microorganisms. This renders the cells unable to replicate before they die. The disinfection stage takes seconds, eliminates the need for chlorine, and makes the final process much safer. At the wastewater treatment plants, more than 90% of the pollutants are removed from the City of Windsor's wastewater before the water is returned to the Detroit River. And that's important because the Detroit River and the surrounding lakes are our primary source of drinking water and so much more.
People cannot live without water. We need water for agriculture, we need water for hygiene, we need water for recreational aspects, we need water for drinking, and we have no substitute for water. It's too easy just to try to pass the blame to somebody else. We're all sharing the same resource and we all have the same responsibility.
Right now, the Detroit River is still considered an area of concern under the Great Lakes Water Quality Agreement.
We have to care and protect for the resource that we're using and that we're leaving behind for our generations as well.
So let's recap. Wastewater leaves your house, gets treated at the wastewater treatment plant, and returns here, the Detroit River, the same place your drinking water comes from. And what does this all mean? For the past 8 minutes, we've shown you how our wastewater treatment system works. We've told you why it's important to pay attention to what you put down sinks, toilets, and sewers. But if your mind's been floating elsewhere, here's what you absolutely positively need to know.
Number 1, number 2, and TP. That's it. That's all that goes down there. Oh, and TP? It means toilet paper. Oh yeah, and this? Soap and water. That's it.
So, hard water is water that contains a high concentration of calcium and magnesium salts. You can also have iron salts. The fairly high amounts of calcium and magnesium in water is not harmful. It can cause several problems. It leads to the formation of scale and eventual clogging inside of pipes. It also inhibits detergent action. So it makes soaps not lather as much, and you get in yellowing bathtub rings and less lathering action. So here is a video about hard water versus soft water.
Hard or soft? How am I supposed to know? They both look exactly the same. Hey there guys, Sapna here for D News. From the outside, all water is seemingly the same. Clear, mostly flavorless, 2 hydrogens, 1 oxygen. But once you get past the basics, water is actually pretty versatile. It can be distilled or filtered, tap, bottled, and if you're really fancy, there's water marketed as kosher, organic, or Kabbalah. But did you know water can also be hard or soft? No, this isn't to describe how the water actually feels. It has to do with its mineral content. Water becomes hard when it has a higher than normal concentration of minerals, primarily calcium and magnesium. Water picks up these minerals from rocks and soil as it flows through rivers, wells, or other waterways. Soft water, on the other hand, has a low mineral content, either because it has not yet flowed through rocks or wells, like rainwater, or because the rocks it has come in contact with have little to no soluble minerals. But that isn't to say that there's a set amount of hard and soft water on Earth. Because of the hydrologic cycle, our water fluctuates between hard and soft. For instance, water that lives in oceans or streams tends to be hard because it's already picked up minerals. But when this water evaporates and later becomes rain, it leaves those minerals behind and becomes soft. It's important to note that water is not just hard or soft. It's a spectrum, with water becoming more hard as its mineral concentration increases. The United States Geological Survey classifies soft water as anything with less than 61 milligrams of calcium carbonate per liter. Above that is moderately hard water, then hard water, and very hard water. According to the U.S. Department of Energy, almost 75% of U.S. homes have water that is at least moderately hard. Probably the best place to see the difference between hard and soft water is in the bathtub. Soap is primarily made of a white solid called sodium stearate, which, with the help of water, carries away dirt and oil. Normally, the components of soap dissolve in water, causing a good lather. But in hard water, the soap reacts with the minerals, forming insoluble compounds. For example, the magnesium in hard water reacts with the stearate to form magnesium stearate. This makes it more difficult to get a good lather in hard water. It also causes the soap scum you see on the sides of the bathtub. Hard water can also leave behind limescale, which occurs when water is heated or when it sits for too long and the minerals solidify as that water evaporates. As you may have noticed in your own home, limescale looks gross and it's really difficult to get off pots and faucets. To avoid this, a lot of people choose to soften their water. An easy way to do this is by boiling water, which causes the calcium carbonate to evaporate, leaving the remaining water soft. However, there is another type of hardness called permanent hardness that cannot be boiled away. Water becomes permanently hard when it flows through rocks with calcium sulfate, also known as gypsum, which cannot be removed through boiling. But despite its name, water with permanent hardness can be made soft. The most common way of doing this is by adding a chemical softener that filters out many of those minerals. But you may not be compelled to do this because beyond difficulties with bathing and some household chores like laundry and dishes, both hard and soft water are generally thought to be safe to drink, cook with, and bathe in, especially if the water has gone through a treatment plant, at least in the United States. However, some cities do choose to soften their water, removing some of these minerals at the water treatment plant before it even goes out to consumers. If you're curious whether the stuff coming out of your tap is hard or soft, take a swig. You can usually taste the minerals in hard water, whereas soft water is a little more flat and can sometimes taste salty. So that covers fresh water, but what about salt water? Why can't we drink it? Trace answers that question here. Got any more questions about water? Let us know in the comments and subscribe to D News for more videos every day.
Sorry about this error, but this is having this problem.
When softening your water, the unit is in the service position. Raw water enters into the tank from the top and travels down through the resin media. This is where hardness minerals like calcium and magnesium are removed from the water. The treated water flows to the bottom of the tank to enter the distributor tube and exits the system to travel throughout your home for use. Once the system no longer has enough capacity remaining to treat the water needed for the day, it will initiate its regeneration sequence at its scheduled time. Regeneration begins with the brine tank fill cycle. Water enters the system to flow through the resin, softening the water before entering the brine tank. The water will stay here, dissolving the salts to create a salt solution called brine that will be used later in the regeneration process. Filling the brine tank with soft water plays a critical role in better performance and less cleaning of the brine tank. The next step in the regeneration process is called backwash. Raw water enters the system through the distributor tube to physically lift up and agitate the resin. This helps clean off any debris or sediment that has been caught inside. The undesirable particles flow out to the drain. After the water has had enough time to dissolve the necessary amount of salt in the brine tank, the solution is drawn back into the system. Our patented chlorine generator activates for a short time to create free chlorine from the salt's chlorides. This helps keep the system clean with every regeneration. The remaining salt solution passes over the media to remove the hardness minerals captured by the resin. One final rinse cycle is used to ensure that any remaining salt is flushed from the unit. When the cycle is complete, the system returns to its surface position to provide quality soft water to your home.
So that's a water softener. Wells tend to have very harder water, but I mean, it varies location to location. So the ocean. Coastal regions of the world are dominantly shaped by the influence of surface waves. So things like shoreline zones that range from rocky cliffs to broad, low sandy beaches. The 5 major oceans of the world include the Pacific, Atlantic, Indian, Antarctic, and Arctic. And oceans cover about 70% of the Earth's surface and have an average depth of around 4 kilometers. And the deepest point in the ocean is the Marianas Trench in the Western Pacific, at about 11 kilometers deep. I think the Challenger Deep in the Marianas Trench is like almost 12 kilometers deep, but I could be misremembering. It's deep enough that it's like legitimately hard to measure the depth. So there are basically 3 types of motion for seawater. These are waves, currents, and tides. So waves are driven by atmospheric winds and occur at the surface of the water, interaction of atmospheric winds on the surface of the water. They're waves on the surface of the water. Waves of various sizes continue to lap the world's shoreline. Currents are large-scale flows of water throughout the ocean. And tides are tides. They're driven by gravity from the moon, the differential gravity of the Earth and the moon. And they cause water to flow in different areas. So you could have places where you have really big tides and places where you have smaller tides. Tides are driven by, so you get 2 tides a day, and they vary throughout the month because of the position of the sun and the moon relative to each other. So for waves, though the waveform will continually propagate throughout the water particles themselves are only moving in small, generally circular orbits. So when you have a wave on the water itself isn't like, if you have a little bit of water in a wave, that water is not going to move to the other side of the ocean or something. Just the disturbance is going to move. And since the water is not actually moving, things like debris will simply bob up and down as the waveform will continually pass under it. So out in the deep ocean, waves aren't that dangerous. They just lift your boat up and then your boat sinks down. Also, they're not as big when the water is deeper. They spread out, basically. As the waveform enters the shallow water along the shore, the underwater circular motion of the wave interfered with, the wave kind of piles up, and this results in surf. So here is a video about how do water waves work. Yep. This error is so frustrating.
Everyone watching this has probably spent some time at the ocean at some point in your life. The sandy beaches, the peace of the ocean, the crashing waves. But what even are ocean waves, and how do they work? Waves are caused by a number of things and contain massive amounts of energy. In fact, just 2% of the total energy of ocean waves could be used to power the entire world. There are essentially 3 types of waves: wind-driven waves, tidal waves, and tsunamis. Wind-driven waves form as wind passes over the surface of the water. Pretty simple. Energy from the motion of the air molecules in the wind is transferred to the top layer of the water through friction and pressure. These transfers of energy cause disturbances in the water that is carried through the water. One thing interesting about ocean waves is that the water isn't actually moving. Rather, it's the wave that moves through the water, in general. This means that as a wave moves through the water itself essentially moves up and down, reacting to the wave energy moving through it. So wind can cause waves through friction and pressure, But there's also another hidden force to certain waves: gravity. Tidal waves are not massive tsunami-like waves like you may be thinking. These are actually just large waves that move across our planet. The gravitational forces of the Earth, Sun, and Moon affect how the water on the Earth behaves. The Moon has the greatest effect on waves as it moves around the Earth. As the Moon moves, it causes oceans to swell on either side of the Earth, or the side closest to the Moon and furthest from the Moon. As the Earth rotates, tides around the world go in and out, as we all probably know. The actual mechanics of this might surprise you, though. The bulge of the water on the Earth stays consistent with the location of the Moon, and it's actually the movement of the Earth that greatly affects tides going in and out. This gives the appearance of high and low tides, when in actuality it's the Earth that's moving, not the water. The last type of waves to discuss are abnormal in nature. Tsunami waves are large, powerful waves caused by geological disturbances like earthquakes, landslides, or volcanic eruptions. Tsunamis are generally very large simply due to their nature and formation. Now that we've gone through the different types of waves, we need to understand a little bit more about the physics of these waves. When ocean waves meet, generally one of three things happen. Sometimes they don't interfere, rather they just add together momentarily, called superposition. If one wave was traveling in one diagonal direction and another in the opposite, the point where they met in the middle of the x would be the height of both of the waves added together. In other cases, waves can cause destructive interference, which occurs when two waves collide with the crest of one wave meeting the other. This is essentially identical to how electronic waves work too, thinking of it as positive and negative. When a positive crest meets a negative valley, they add up to zero. They cancel out. The last possible interaction of the waves is constructive interference, which occurs when two waves collide and the crests align. When this happens, the waves add together to become one massive wave. Finally, when a wave hits a shore or beach, in most cases, the land can oppose the force of the wave and causes it to expend all of its energy. This causes the wave to come crashing into shore, bringing us full circle back to the peaceful beaches we all know and love. So that's how waves work, through wind, gravity, and sometimes volcanoes.
So, as a surface wave approaches the shore, underwater circular motion becomes elliptical, and finally the crest will fall forward. That's how you can get those waves arcing over. Tides are the periodic rise and fall of the ocean surface caused by the gravitational pull of the moon and to a lesser extent the sun. And the size of the tide is really because, as mentioned in the previous video, you have the Earth rotating under this bulge of water. If you have a structure that channels that water into a certain place, you can have really big dramatic changes with tides. So in some areas of the world, the daily tidal range may be as much as 12 meters. In others, it's less than 1 meter. And there are tides on Lake Michigan. You can look them up if you want. And you get basically 2 high tides a day, 2 low tides a day as the Earth rotates through the 2 lumps. And waves, longshore currents, and tides are all important agents of erosion along coastlines. And we'll watch this video on YouTube as well.
In 1999, the German newspaper Die Zeit ran an
Supposed to happen. Sorry, I misclicked. Like,
This shows 12 hours at the famous Bay of Fundy in Nova Scotia, Canada. It's the biggest tide change in the world. But what force could move such a massive body of water? Gravity.
Here's the Earth rotating on its axis every 24 hours. We'll now draw the Earth as a diagram with its surrounding layer of ocean. And to the right is the silvery moon. Everything is attracted to everything else in the universe with the force of gravity. So the moon is attracted to the Earth, and the Earth is equally attracted to the moon. Notice that the two force arrows are the same length, showing that gravitational attractions are of equal strength. But we're only interested in the force on the Earth here. The moon pulls on the ocean closest to it and makes it bulge outwards. When the Earth rotates, the sea level is higher at this point in its rotation, causing a high tide. And a low tide where the oceans don't bulge. So you'd expect one high tide each day. But here it gets interesting because there are two high tides a day. How come? This is because the strength of gravity is greater when objects are closer. We'll call the location of the ocean on the near side of the moon, point A, at the centre of the Earth, point B, and at the far side ocean, point C. The strength of the moon's gravity is strongest at A because it's closest to the moon. So the part of the ocean that bulges towards the moon most is at A. But the moon's gravity also pulls on the Earth, moving it towards the moon as well. This has two effects. First, it makes another bulge at C. Second, it fills in the bulge at A, but not completely, because A has moved further towards the moon than B. Lastly, the far side ocean at C is also attracted to the moon, but it moves least because the moon's gravitational pull here is at its weakest, being farthest from the moon. This leaves a partial bulge at C, though not as big as the one at A. Now we can see why, when the Earth rotates through 24 hours, it goes through two high tides and two low tides. But there's another surprise. By the time the Earth has rotated once and arrived back at its original position, the Moon has moved on a bit because it's orbiting the Earth at the same time. That means that the Earth has to catch up with the Moon, so the next day's high tide is about 50 minutes later. The Moon rises and sets about 50 minutes later too, because the Earth has to catch up with its orbiting Moon. You can even test this by timing the moonrise or moonset from one day to the next. Or check out some tide charts to see if the tides obey this rule too.
So, along irregular coastlines, a number of different features will form. And the portions of the coastline that jut out the most get subjected to the most intense wave energy, so they get more erosion. And when a coastal area is elevated, if you have like a cliff, the wave action can only attack the base of the slope below the high tide level, which means it wears away at the bottom, and eventually the top will collapse. So you get wave-cut cliffs, sea stacks, sea arches, and sea caves all can form in this process. So here's a video about some of the features formed by coastal erosion.
The continual battle between land and sea is apparent here, along the northwest coast of America, where erosion is the predominant force. Millions of years ago, this coastline would have looked very different. Even though the land is tough basalt, the relentless attack of the sea has eroded it in spectacular ways. Cliffs are formed when weathering weakens the top of the land, and destructive waves attack the bottom of the rock face. Weak points in the rock are affected most, and eventually form a hollow, called a wave-cut notch. The overhanging rock collapses, and the rubble is carried out to sea, forming a wave-cut platform. The whole process continues, causing the cliff to slowly, but continually, retreat. But erosion also produces more unusual features. Hollow caves can be carved out by the water and eventually break through, forming an arch. The continual erosion keeps widening the arch until it can no longer support the land on top. The arch collapses and leaves a headland on one side and a tough outcrop of rock on the other, called a stack. Whilst erosion constantly attacks our coastlines, deposition builds characteristic landforms. When constructive waves wash onto the shore, they dump material carried in the water, like sand, pebbles and rocks. This builds up beaches. Whether a beach is soft and sandy or hard and pebbly depends on both the wave energy and the local geology. A narrow, extended stretch of beach that projects out to sea is called a spit. These are formed by deposition as well, but wind conditions also have a part to play. Where the prevailing wind blows at an angle to the coast, it causes longshore drift. Material is moved along the coast at an angle. Over time, the wind and waves affect the end of the spit, causing it to curve to create a hook end. This creates a sheltered area protected from incoming waves. Silt is deposited and mudflats or salt marshes can form. Erosion and deposition have created the world's beautiful and dynamic coastline and continue to affect these ever-changing landscapes.
So here you have an elevated coastline. You have cutting from the waves, basically. You can get sea caves, sea arches, sea stacks. And because the erosion is all below the high tide mark, you get these wave-cut cliffs that are sort of undermined. So here's a sea stack and a sea arch. When that overlying arch collapses, you get the stack. Now, shoreline sediments come from either shoreline erosion or from stream transport, and then these can be deposited along the shore, distributed along the coast by waves, longshore currents, and tidal action. And this sediment deposition occurs along calmer stretches of the coast and results in several characteristic forms. Some common depositional features include pocket beaches, where a little pocket fills in with sand, barrier islands, which are these strips of islands along the edge of the coast that help protect the inland coast, lagoons, and spits. So here are videos about these depositional features.
Again, submerging coastlines do not exclusively have depositional or aggradational landforms. They may very well have erosional landforms or degradational landforms, but submerging coastlines are dominated by depositional landforms. These are the ones I want you to know. Really? It's a bunch of sand. Of course, a beach. I mean, I don't even know how to define the thing, to tell you the truth. A spit is a beach that stretches partway across a bay. A bay mouth bar is a beach that completely encloses a bay. So if a beach is stretching part of the way across the bay, it's a spit. If it completely encloses the bay, it's a bay mouth bar, like Bolsa Chica Beach in Southern California. And a tombolo, this is a name that I use if I want to check into some place and I don't want people to know that I'm famous. So I'll check in rather than as Bill Quarter, I check in as Tom Bolo. A tombolo is a beach that connects a sea stack to the shoreline. All right, left-hand side, you've seen that before, that's a beach. Now if you look at the right-hand side, that white arrow is pointing at a spit. Can you see what happens here? The wave action forces this sand out here, creating this spit, this kind of hook that hangs off there. And if you look carefully, you can see down here on the bottom of this photograph, the way the beach is being stretched out. This is indicating that the current is coming in this direction, and the waves are tending to break in this direction, which is pulling the sand out into that bay of water. These are also spits. You can see there's a spit going along here. Notice that this area right here, behind the spit, the waves come in, crash along the beach, but this area, because it's now protected by the spit of sand, is beginning to fill in. Vegetation, materials of earth type, like sand and rocks and gravel and alluvium are all going to be deposited there, which slowly fills that area in. You can see the same thing over here with this spit. And in fact, there's houses that are built here because the beach itself is protecting this area from the waves. And as a result of that, vegetation can grow there and the area can sort of develop into either urban development, or you can leave it as wetlands or whatever it's going to be. This is a bay mouth bar. You can see that bay mouth bar. See the way the bays are back here? And the beach stretches along there, completely enclosing this back bay area. Typically, as this fills in, like we just saw a second ago with the spits, the type of vegetation that grows in that type of area tends to be halophytic vegetation. Halophytic vegetation, like this mangrove swamp, halophytic vegetation means that the vegetation is salt tolerant. This comes from halite, which is salt. And hydrophytic vegetation. Hydrophytic vegetation is vegetation that lives in water. So all vegetation, or most of it, is going to need water, but this literally is living in water. Like, for example, seaweed or kelp is both hydrophytic and halophytic, but I'm talking about vegetation that's on land. Then you can see that black arrow is pointing at a tombolo. The tombolo is the beach that's connecting this sea stack, Morro Rock right there. It's connecting it to the shoreline. Otherwise, this would be an exclusive island out here. But this beach stretches out and connects Morro Rock, which is a sea stack, to the shoreline. The beach is the tombolo.
Okay. Coastal Georgia line. Nope. Oh. This is what I want. This is going to have the same error. Oh. Really, really, really.
Well, we are here at Fort James Jackson. The Savannah River is behind me. To this direction is the city of Savannah, and this way is the Atlantic Ocean. So when we talk about the early history of Georgia, we really can't talk about that without talking about Georgia's barrier islands. There are 14 barrier islands that count as the outer barrier islands for Georgia. Coastlines generally have barrier islands, so they go all the way down the east coast of the United States along the coastline. Georgia's barrier islands are sometimes called the Golden Isles or the Sea Islands, and geographically they're made of sand and they have sand ridges, and they're constantly being changed by wind and water. So tides, storms, and anything like that will change the shape of those islands, but they will always be there sort of protecting the coastline from weather and from erosion. They generally are separated from the mainland by about 4 to 6 miles of salt marsh, and sometimes that can include woods, like marine woods, things like that. And they're pretty diverse as well. Like some islands will have more sandy beach and other islands will have more woods, just depending on the location and how the weather is in those areas. Now, the barrier islands here in the southern United States, especially ones by Florida and sort of the southern Georgia barrier islands, in the early days before European colonization, you're going to have Native Americans living there. Generally, in the northern part of Georgia, or what is now Georgia, you would have Muskogee-speaking creeks and then Timucuan-speaking creeks as you move further south. Now, as early as the 16th century, there is a Spanish colonization in the barrier islands. They use it for mission work, and they do spread a Catholic religion there to the Native Americans, but it's also a way for them to sort of bring the native peoples into Spanish colonialism. So there's a little bit of a conflict between the Spanish and the English a little bit later on.
Okay. Okay, so here are some features of coastal deposition. The form, you can have barrier islands, you can have spits, you can have pocket beaches, things like that. The pocket beaches form in low energy protected zones between coastal headlands where sand settles out. Barrier islands are long, narrow deposits that form parallel to the mainland. Both North Carolina and Texas have a number of barrier islands separated from their mainland, and lagoons form between the mainland and the barrier island. Spits are elongated extensions of the shoreline. So Cape Cod, Massachusetts is a classic example of a spit. So here is another video about coastal erosion features.
When wave energy is high, coastal erosion takes place, resulting in a variety of coastal features. The rate of erosion is moderated by the mixed geology of the coastline. Hard rocks such as basalt are more resistant and thus erode much slower than soft sedimentary rocks such as limestone. We call this differential erosion. Coastlines that have an alternating geology of harder and softer rocks results in the formation of headlands and bays, as can be seen here in Port Macquarie. The places where the rock is harder has headlands jutting out. Where the rock is softer, more erosion takes place and bays form. Over time, the headlands become more exposed to the erosive power of waves due to wave refraction. This occurs because the waves slow down first in shallower water, forcing the refracting part of the wave to break first at the headland, while the other part of the wave is travelling faster towards the beach in deeper water. The erosion at headlands results in the formation of spectacular coastal features such as cliffs, wave-cut platforms, arches, caves, blowholes, and stacks. When large amounts of water are constantly hammering away at the coastline, the processes of hydraulic action and abrasion can cause cliffs to retreat and create a feature called a wave-cut platform. Wave-cut platforms are broad, flat areas of rock that are often found at the base of cliffs and headlands. At the edge of the platform there is an escarpment. Hydraulic action is when waves smashing against cracks and joints in the rock compress the air in those cracks. The pressure created by this can eventually cause fragments of rock to break off. Abrasion occurs when wave action transports sediment which hits the cliff and gradually wears it away. Attrition also takes place where the waves cause rocks to rub against each other. As this happens, the original rocks reduce in size to smaller and rounder fragments. As these processes take place, a wave-cut notch can form at the base of the cliff. The notch forms because the force of waves is only eroding the rock between the high and low water mark. This causes the rock below the low water mark to remain. Over time, this notch gets progressively bigger until the cliff eventually collapses. As a result of collapsing cliff faces, there is a lot of debris at the base made up of large boulders. In these places, the debris from collapsed cliffs is broken down by waves. The backwash carries the debris towards the sea, forming the wave-cut platform. Then the whole process repeats and the cliff continues to retreat. Understanding the workings of erosion processes such as cliff retreat is very important for people as they impact heavily on any human coastal development. For caves to form, there must be a weakness in the headland's rock, such as a soft rock type or an existing crack. Over time, hydraulic action makes these cracks bigger and bigger until a cave forms. Sometimes a cave roof will partially collapse to form as a blowhole, such as this one here. Other times the wave will erode the cave right through to the other side of a headland to form an arch. Eventually, the ceiling of the cave will completely collapse, causing part of the headland to detach and form a vertical column of rock in the sea known as a stack. Another peculiar type of erosion feature found on rocky shores around the world is called honeycomb weathering. This formation is caused by salt crystals getting into cracks in the rock. Sea spray and winds are the usual ways for salt water to make its way into these places. When the water content evaporates, salt crystals are left behind. The rocks go through a wetting and drying process as they are often found in intertidal zones. When they dry from the sun, the crystals heat up and expand, which puts pressure on the confining rock.
So, let's talk about the seafloor. We talked about the coast. Let's talk about the seafloor. So before modern technology revealed a detailed view of the ocean floor, most scientists thought the floors of the ocean were relatively smooth and covered in sediment. We now know that the topography of the seafloor is just as irregular as the surfaces above sea level. There are some, beneath the waves, there are submarine mountain chains, isolated volcanic mountains, trenches, and extensive flat areas. So submarine mountain chains form along divergent plate boundaries and are called mid-ocean ridges. These are places where new sea floor is being formed. Volcanic mountains are known as seamounts and form over isolated hotspots like the Hawaiian Islands. And some submarine seamounts have unusually flat types and are called guyots. So guyots were originally volcanic islands that broke the surface, had their top eroded away, and then the sea level around them changed. And so they have this really flat top because of that. Seafloor trenches are another significant feature found under the oceans. These trenches are generally long and narrow and mark the location of submarine subduction zones. And continental erosion supplies huge quantities of sediments onto the seafloor, and these sediments have the tendency of covering and or masking some of the irregular seafloor features. The huge flat areas called abyssal plains form from this influx of sediment. So here is a video about the topography of the seafloor. And as usual, it is failing.
Geoscience Australia provides specialist advice, knowledge and capability in response to some of Australia's most important challenges. This includes managing the nation's marine jurisdiction and maintaining geoscience knowledge and capability. Geoscience Australia is supporting the multinational search effort to find missing Malaysia Airlines flight MH370. Its scientific teams provide advice and expertise to Australian government agencies, the Joint Agency Coordination Centre, and the Australian Transport Safety Bureau. This collective effort has enabled the mapping of over 200,000 square kilometres of seafloor in a remote area of the southern Indian Ocean. Undertaking a search in an area of this magnitude, remoteness and complexity is an involved process which draws on multiple techniques, technologies and experts from a range of disciplines. Previous maps of the MH370 search area have been derived from satellite data, only providing an estimate of the ocean depth. Such low-resolution maps cannot safely guide navigation during an underwater search, which requires more detailed knowledge of underwater features. A high-resolution map can be created through a comprehensive bathymetric survey, which collects high-resolution data from the seafloor. Bathymetric data is gathered through the use of multi-beam sonar equipment mounted on a ship's hull. The sonar system sends out multiple sound waves that bounce off the seafloor and return to the ship. The delay between sending and receiving a signal provides a measurement of ocean depth. The strength of the return signal provides an indication of how hard the seafloor is. The ship proceeds through the search area in overlapping lines to systematically capture depth information. Overlapping the lines increases confidence in the accuracy of the mapping and helps to address gaps in the data, which may occur due to factors such as bad weather. Scientists working at Geoscience Australia review, correct and analyse the data to create three-dimensional models and maps that reveal details of the seafloor. Bathymetric mapping during the search for MH370 has revealed a detailed picture of the underwater landscape, identifying potential hazards to navigation within the search area. These include large mountains and deep trenches, some of which plunge to more than 6,000 metres below sea level, along with seamounts and ridges, like this one, which is 34 kilometres long. The bathymetric map is an essential navigation tool for the more detailed underwater search. Using the bathymetric map to safely navigate at a much closer range to the seafloor, the Joint Agency Coordination Centre and the Australian Transport Safety Bureau carry out the underwater search. Search vessels slowly tow a small submersible vehicle or towfish on a cable around 10 kilometres long. The towfish descends thousands of metres down through the water until it travels approximately 100 metres above the seafloor. The towfish operates a side-scan sonar that maps features on the seafloor in much greater detail. It gathers data up to 1 kilometre on either side of its path. The side-scan sonar sends out pulses of sound that reflect off seafloor features. Some types of material, such as boulders, gravel, volcanic rock or metal, reflect the sound waves more strongly than fine sediments like clay and silt. To accurately capture data, the towfish travels at very slow speeds of only 3.5 kilometres per hour. Interpretation of the captured data produces images that resemble black and white photos and reveal a great degree of detail about features on the seafloor. The collection of this highly detailed data aims to identify any crucial evidence of the missing aircraft. Scientists and experts from many and varied disciplines continue to work together to assist in the ongoing search efforts for MH370. The different types of data acquired and analysed through their efforts has proved critical to understanding the environment in which the search is operating. In future, data from the bathymetric survey will also form a permanent record of this deep ocean and contribute to new scientific knowledge and understanding.
Okay. So, continental shelves. Most of the oceans are underlain by oceanic crust and thus contain very deep columns of water. Continental crust, however, does extend and underlie some areas near the continents. In your Pangea lab, those are those darker shaded areas around the edges of the continents. Portions of the ocean underlain by continental crust are called continental shelves. These zones are much shallower than the oceanic basins, and the width of the continental shelf area varies from almost nothing to over 1,200 kilometers, depending on where you are. Continental shelves are of particular economic interest to the bordering countries for a number of reasons. They provide most of the major commercial fishing zones throughout the world because they're shallower. You can get certain types of fish there. In addition, continental shelves are locations for significant offshore oil deposits and serve as areas for future potential oil reserves. So here you have the continent. You have a lower area that's the continental shelf, and then there's this drop off at the continental slope into the actual oceanic crust, and then there's a pile of sediment there. So the continental slope actually marks the true edge of the continental landmass, and sediments erode off the continental shelf and accumulate near the base. Beyond the continental shelf, the seafloor slopes more steeply downwards to the floor of the ocean basin. From a plate tectonics view, this continental slope marks the transition from continental crust that's less dense to oceanic crust that's more dense. So let's go through a review of chapter 23, and then we'll be done for the day. Remember, we have the tests next week on Monday, and starting at 10, the quiz for chapter 23 will become available on Blackboard, and you have that available for a week. So what do we call the breakdown of rock by various processes such as rain, wind, and temperature fluctuations? Weathering. The two types of rock breakdown processes are physical weathering, breaking into little pieces, and chemical weathering, being decomposed chemically. The cycle of freezing and thawing water in rock cracks is called frost wedging. The portions of the soil that are in a constant frozen state are called permafrost. When rock material interacts with water, creating chemical reactions to occur, this is an example of chemical weathering. The rock breakdown process in number 5 works most efficiently in hot, wet climates because you want water and you want heat that makes chemical reactions go faster. What acid is formed when water reacts with the free carbon dioxide in the air? That is carbonic acid. What common mineral in limestone does the acid referred to in number 7 react with? That is calcium carbonate or calcite. How quickly does chemical weathering occur in polar regions? It occurs slowly because of the cold. What common igneous rock is very resistant to chemical weathering? Granite. The downward movement of weathered material due to gravity is called mass wasting, or just mass movement, but mass wasting. Rain that doesn't have enough time to be absorbed by the ground is called runoff. The flow of water that follows a definite path between two banks of land material is called a stream. Materials both dissolved and undissolved that are carried by the stream are called the stream load. The 3 types of stream load from largest to smallest particles are the bed load bouncing along the bottom of the stream, the suspended load carried in the water, and the dissolved load dissolved in the water. Is the upstream section of a stream the origin of the stream or the end portion of the stream? Is the origin of the stream. Upstream is where a stream starts. In the upstream area, you get a V-shaped valley. That's the shape of valley you get in the upstream area. The lower limit of a given stream that it cannot erode anymore is called the base level. The widened valley floor that comes about due to excessive flooding is called a floodplain. Twists and turns in a stream's path are meanders. The stream speed is greatest on the outside of a bend and slowest on the inside of the bend. When a loop of these bends is cut off, you get an oxbow lake forms. The sediments of a stream or river eventually end up in the ocean, or they get deposited in whatever body of water it dumps into. And the buildup of sediments near a river endpoint can produce a fanned out area called a delta. Glaciers form when the rate of snowfall in an area is greater than the rate of snow melt. Glaciers that cover large sections of land, such as Greenland, are called continental glaciers or ice sheets. Small glaciers that are found in mountainous areas are called cirque glaciers, or the general term for mountain glaciers is alpine glaciers. You have cirque glaciers here. Glaciers found in mountainous syncline areas are referred to as valley glaciers, because they're in valleys. That's what a syncline is. A syncline is a dip. Sediment that is deposited at the furthest point of a glacier's advance is called an end moraine or a terminal moraine. Wind is very effective in desert environments. The downward movement of rock and soil due to gravity is mass wasting. The rapid downward movement of large amounts of weathered material is called a landslide. The rapid downward movement of water-soaked soil is called a mud flow. The slow movement of unbroken material is called slump. The very slow movement of debris is called creep. The constant changes of phase that water undergoes, this is known as the hydrologic cycle, or the water cycle. Around 98% of the Earth's water is found in the oceans. Most groundwater is used for agriculture, and most of the groundwater is used for agriculture and for human consumption, and some for industry. Groundwater is stored in rock material with small spaces called porosity, called pores. The degree that the rock has these small spaces is called the rock's porosity. Rock that allows fluids to be transmitted through it would have a high level of permeability. Due to gravity, water moves through the zone of aeration until it reaches the zone of saturation. And the boundary between these two zones is known as the water table. Wells can tap the water available in the zone of saturation. Impermeable rock that is capable of containing groundwater is called an aquifer. I would say permeable rock there, but no, impermeable. I don't know. If groundwater flows to the surface under its own pressure, you have an artesian well. The rate of water replacement in an aquifer is called the rate of recharge. If too much water is removed from the zone of saturation, ground subsidence occurs. Freshwater being less dense than salt water, it stays on top of the salt water normally. Hard water contains many of the ions of calcium and magnesium. Coastal regions are susceptible to surface waves. The three types of seawater movement are tidal, current, and wave. Tides are formed primarily by the gravitational pull of the moon. Structures can be formed near shorelines due to the erosion of rock material. The weathering of rock material and the erosion of rock fragments. The ocean floor was once thought to be a smooth surface, but we now know to have a very irregular bottom. Sorry, we went over time. We were running a little behind on other things, and then we had the problem with the videos. So, test is on Monday. It'll be mostly multiple choice with some short answer. The chapter 23 quiz will be up on Blackboard starting today at 10, and it'll be up until the 9th. You have basically a week. And you have the chapter 22 quiz today in SI, and you can pick up your graded labs there. And if you need to turn in a lab, I'll take it. That's all. You're free to go. Sorry, I ran over. Now I get to try and figure out what the stupid error is, and it may not be fixable, which is extra annoying. Yeah.